Hello everyone, I'm Yonong Park from Seoul National University. In this talk, I'm going to present a paper titled Ginex SSD-enabled billion-scale graph neural network training on a single machine via Provably optimal in-memory caching. As you all know, graph is everywhere. Graph data plays an important role in many diverse domains. Therefore, many different methodologies to analyze graph dataset have been proposed. Graph neural network is one of them. GNN tries to solve various inference tasks on a graph by using neural network. In general, GNN operates on a graph where each node has its own feature vectors. Feature vectors represent unique property of the node. For example, in social network graph, feature vectors will be values that represent user's gender, age, affiliation, and so on. The unique property of GNN is its input. When it processes a certain node, which we call target node, it takes the feature vectors of not only the target node, but also the neighbors of target node as input. For example, when user 1 is the target node, the feature vectors of user 2, 3, and 5 are fed as input along with the feature vector of user 1. By synthesizing the neighborhood information, GNN outputs a semantically rich embedding for the target node, which can be used for various downstream tasks. Although this example considers only the direct neighbors of the target node for simplicity, it is common practice to reflect 2 or 3 hub neighbors. Now I will explain the GNN training systems. In general, just like other types of GNNs, the model is trained with mini-batch gradient descent and the computation is accelerated by GPUs. Mixed CPU-GPU approach is popular, where CPU prepares data while GPU performs computations. The whole training process consists of 4 steps: sample, gather, transfer, and compute. First of all, sample is to find neighbors of the target nodes by traversing adjacency matrix. Gather is to collect feature vectors of the nodes extracted from the sample stage in a contiguous memory buffer. The collected feature vectors are then sent to GPUs, where forward and backward computations are performed. One of the biggest challenges of GNN training is the size of graph. Graph dataset includes both adjacency matrix and feature vector tables, and their size reaches up to hundreds of gigabytes or even few terabytes. Graph dataset with such a size does not fit in a single node memories. There are 2 possible approaches to deal with these memory capacity issues. First one is to scale out. By making a cluster of multiple nodes, one can keep graph dataset in memories. This approach has been studied for years and it is good for performance. But this approach may increase the system cost a lot. The other approach is scale up. Instead of having multiple nodes, one can keep graph dataset in high-capacity storage devices like NVMe SSD. This approach has hardly been studied because it is too slow. The focus of our work is this approach. In this work, we try to speed up this approach as much as possible and thus suggest a cost-effective option for large-scale GNN training. To see the bottleneck of SSD-based GNN training, we profiled its training time. We used graph datasets much larger than the main memories. Graph datasets are kept in SSD and memory mapped by mmap syscode. As expected, data preparation, which is I/O-intensive part, was the bottleneck. Especially, gather was the main bottleneck as it generates more than 90% of the I/O traffic. Along with the training time breakdown, we also profiled the page cache miss ratio. As expected, page cache miss ratio was so high, it reaches up to almost 90%. From this observation, we conclude that we need a better in-memory caching mechanism, especially for feature gathering. So we proposed Ginex. Ginex is a GNN training system for efficient training of a billion-scale dataset on a single machine by using SSD as a memory extension. Ginex boosts the performance of SSD-based GNN training mainly by 2 technical contributions. First one is a reconstruction of GNN training pipeline for realization of optimal in-memory caching mechanism for feature gatherings. And the second one is an efficient implementation of the optimal cache replacement policies. I will first cover the pipeline reconstructions. This is conventional pipeline of GNN training. In the conventional pipeline, Sample operations are performed in parallel to the others like gather by having separate processes. Ginex Pipeline, however, abandons these parallelisms. Instead, Ginex first performs sample operations for a group of batches which we call superbatch. Only after the sample for the superbatch finishes, Ginex enters main loop where the remaining operations like gather, transfer, compute are performed iteratively. The reason for such a pipeline is that the result of sample indicates which feature vectors to access at the corresponding gather. For example, the feature vectors to be accessed at the first gather is the one sampled at the sample one. The same goes for the next batches, like this. Therefore, the result of superbatch sample is data access traces of the following gather operations. By analyzing these traces, we are now able to implement optimal caching mechanism for gather operations. Then let's dive into a little bit more details of Ginex pipelines. At runtime, Ginex iterates 4 stages. Between superbatch samples and main loop, there are 2 more stages named Changeset Precomputation and feature cache initialization. At first, by traversing the adjacency matrix, Ginex performed superbatch samples and saved the result back in SSD. Next, by analyzing the superbatch sample result, Ginex computes changeset for each iteration of the following gather operations. Changeset refers to what to insert into and evict from the cache at each iterations. This process is accelerated by GPUs. The computed changesets are then saved in SSD. Then, Ginex initializes feature cache and performs the remaining operations like gather, transpose, and compute in main loop stage. One thing to note is that there is one more operation, which is cache update right after gather. By reconstructing the pipeline, Ginex enables the optimal caching for feature gatherings. But to realize it, Ginex additionally introduces one more stage named Changeset Precomputation. Not to make it a bottleneck, it is important to implement this stage very efficiently. So we invented an efficient algorithm for Changeset Precomputation. As explained earlier, changeset refers to what to insert into and evict from the cache at its iterations. To compute changesets, we have to simulate the sequence of cache stage following Belady's algorithms. Belady's algorithm is an optimal cache replacement policy which always evict data that will not be accessed for the longest time. So the problem of cache state simulation can be expressed as this way. To get the cache state of iteration i+1, which you call as ci+1, from the cache state of iteration I, or ci, we first union ci and idis I. Idis I is the node IDs to be accessed at iteration I. Then, we should pick out the ones with the smallest reuse distance among them. And we call this function as fBeladies. Union is easy to implement, but the problem is this one. To solve fBelady, we need to know when each node is accessed next at each point of time. A naive approach is to examine all the future data access traces every time. However, it is very inefficient. Its worst case complexity is S-square, where S is the superbatch size. Ginex, however, incrementally tracks its node's next access iterations. With 2 passes, Ginex builds 2 data structures which are specially designed for incremental tracking, and finish the cache state simulation at the last pass with this incremental tracking. This is the high-level overview of the incremental tracking of the next access iterations. As I mentioned, Ginex maintains 2 data structures. One is called ethers. Ethers is the 1D arrays that lists the access iteration of the nodes in orders like this. At its very start, ethers lists the access iteration of node zeros, which are iteration 1, 3, 9 in these examples. Next, it lists the access iteration of node 1, which are 0 and 4. The same goes for the last. The other data structure is PTR. It has n entries where n is the number of the nodes. At initialization, its entry points the start of each node in ethers, which corresponds to the first accessed iteration of each node. Building these two data structures requires two passes about the access traces. At the last pass, Ginex performs cache state simulation by incrementally tracking the next access iteration of the nodes. For this purpose, at each iteration of the simulation, Ginex updates PTLs in a way that its entry in PTL always points to the next access iteration of each node. It means that we can track next access iteration of the node with these expressions. At the start, the next access iteration is the first access iteration. Before moving on to iteration 1, PTR value for the nodes which are accessed in iteration 0 like node 1 should be updated. The next access iteration of node 1 is not 0 anymore. So, PTR value for node 1 is incremented by 1, like this. At the end of the iteration 1, same as before, PTR value for node 0 is incremented by 1. In this way, the next access iteration of each node can be easily accessed by looking up ethers with PTR values. Such incremental tracking process is accelerated by GPUs and it allows very fast cache state simulation. Please refer to the paper if you want to see the end-to-end algorithms for Changeset Precomputation. Also, you may find other details of Ginex like policies of neighbor cache, structure of neighbor and feature cache, super batch level pipeline, and Ginex configuration in the paper. Now let's move on to the evaluation. I'm going to introduce two key results. First key result is the comparison with single node baselines. We compare Ginex with two baselines named PyG Plus and Ali Plus PG. PyG Plus is a simple extension of PyG which memory maps out of memory graph datasets. Ali Plus PG is the combination of two SOTA works which cache hot parts of graph dataset with static analysis. We use an 8-core CPU with 64 GB memory and 4 billion scale datasets. For all cases, Ginex demonstrates the best performance. You can find out that Ginex alleviates the substantial part of the bottleneck in data preparation. The second key result is cost comparison with distributed training. We build an 8-node cluster for distributed training as well as single-node Ginex instance on Google Cloud. In the case study with two datasets, Ginex reduces the training cost by a factor of 2.76 and 5.71 compared to the dist-dgl, a popular GNN distributed training library. Here is the summary. In this paper, we analyzed the bottleneck of SSD-based GNN training in depth, proposed a novel GNN training pipeline for optimal in-memory caching for feature gathering, and proposed an efficient implementation of optimal cache replacement policy simulations, and demonstrate substantial performance gains of Ginex using 4 billion scale datasets. Ginex is open sourced, and here is the link. Thank you.